We have to work on that. We have to increase our banter capabilities.
Exactly.
So well, we'll just have ChatGPT write us a script so we can get really, really funny. So, all right. Okay, folks, here we are again. I am once again, oh gosh, I should probably say, hey, y'all, it's Dr. Noah.
And I promise we'll keep it short.
Hey, y'all, it's Dr. Know-It-All. Dr. Scott Walter is with me again. We are going to do a follow-up to a very popular video, which has about 77,500 views right now. If you haven't seen it yet, you can check it out up here, or I'll put it at the end of the video. You should definitely check it out. But Scott has, I don't know, I think we need to give you more work or something, because apparently you spend a lot of time manually integrating the acceleration curve of the Starship. So we're going to get some really cool analysis here and look at how underpowered Starship was compared to probably what it should have been. So take it away.
Right. So we had a hot take on Thursday on what was going on, and obviously a lot more information has come out since then. So we can kind of review a little bit of what we may have sort of speculated at the time and what we know is actually factual now, to try to set the record straight, and also take a little bit closer look at what the trajectory sort of looks like of what was going on, to get an idea of whether it performed nominally or not, and about where we were. So I'll explain that in a minute, but I think first what you might want to do is go ahead and share the first screen over here, which I think
should be popping up any second here.
Yep.
Cool. Yeah. Also, you have some stuff on the FTS system, which I didn't realize had been fired off quite as early as it was. So anyway, cool.
Yes. So I brought this into Camtasia just so we can go through it more easily in the frame by frame, because I ended up using it for literally frame by frame, which I'm going to explain a little bit what it was I was doing. But at the beginning, we noticed when everything started to blast off, the first comment we made is like, wait a minute, there's some stuff going up. And I think if I go back and forth, you should be able to easily see that there are some items, like there's an item here and a couple of these others that are very clearly going up very early with the rocket. That's some of the debris that's coming from stage 0. And I suppose what's sort of strange at first is that you expect everything to spread out. Why is stuff going up? And it's because you get so much overpressure there. You're going to have an updraft as well. And so the updraft is going to take any objects which are very light and definitely bring them up.
Well, I don't know, Scott, did you see the Angry Astronauts video from yesterday? Because there was also plenty of stuff that went sideways too. So.
Yes. Yeah. So there's definitely a lot of stuff that goes sideways. I was kind of perplexed. I was like, how could the stuff be going straight up? Because you were expecting it to go out that way. And you can see these chunks here, they look kind of rectangular in shape. They're also dark. They look like they might be thin. So I'm assuming they might be, sheet metal, something very, very light. But there is one object like this one right here, which takes kind of a parabolic trajectory. I don't know if that's a piece of concrete or not. It looks a little bit heavier than the others. It seems to be going more on that ballistic kind of trajectory. So that is possible, something like that. Now, I speculated after some of the pictures started to come out from stage 0 and the aftermath or you are appropriately calling ground 0.
Yeah. So I think after the launch, it is officially ground 0.
Yes. So Michael Baylor at NASA Spaceflight posted this picture here. And when I looked at it, my first thing was like, oh my goodness, this must be the sheet metal and everything we saw flying up, because it looked an awful lot like what we were going up there. And it's like, not too fast, Scott, because this picture was taken Monday by me. So you can see that right there, that was never there to begin with. So some of the things we think are missing actually are not. They were just never there in the first case. But there was something that was going up. And I was speculating when I was there Monday, I was looking at this, and there's also a guard shack off to the side that looks a bit, well, not necessarily ramshackle. It probably is now. But my understanding is this is not there anymore. Right. And this sign here, Angry Astronaut, did find it over on the other side. And that's not a surprise, because I'm not sure what kind of tie-ons they actually used for that. It was going to get blown over the other side. But a lot of the fencing and everything else is gone. So it's more than just that things are getting destroyed there. The fencing itself, I think you would like to survive more than one launch. So if you're going to secure the area, you don't want to have to keep on rebuilding everything around there. So you're going to have to find some way to be able to make sure that exhaust plume does not affect everything that's down at ground level.
Right. Can you go back to that post-launch? Because I'm curious about those big steel panels that it looks like.
I think this was also, not there previous. So I don't think that was ripped off.
Right.
And none of these things were here. So some of the other pictures that you just see ahead of time. Now, there's a question about this, whether that was covered up or not, and what else is going around.
Right.
So it may actually be more intact than we think. But clearly there was some debris, some heavy pieces, or I guess lighter pieces that were able to get pulled up with that updraft. And fortunately not cause any damage directly to the rocket that we're aware of.
Right. Well, except that there is potentially, because we had speculated in talking earlier, we'd speculated that the 3 engines that went out may not have been out immediately, which otherwise they probably wouldn't have released the clamps.
Maybe not. That's something an angry astronaut was wondering about, is that he thought that they were already out before they released it, in which case, if that was NASA, you would not have released it. But then again, they have 33 Raptors, so 3 of them going out, you still have 30 that should be able to give you enough thrust, because the rated thrust is 1.5 times thrust to weight. But at 90%, it's only 1.35. Right. But then if you lose 3 of them right away, you're 1.22, which is about what a normal rocket is. It's about 20% more than the actual weight of the vehicle to be able to go up. So they definitely were, at that point, should have been, and I think we can conclusively show that they probably were, that they had sufficient thrust at that point to be able to launch.
Right.
Okay, so now there is a side view. I forgot to kind of bring it up, but right at the beginning, it's hard to tell from this because it's right on here, but the rocket is actually coming towards you at this point. So rather than going straight up, it already was moving out to sea just a little bit. And we sort of wondered whether that was pre-programmed or not, and they say, yes, it was.
Right.
So the very first thing they wanted to do was get a little bit away, and then once they get past the tower, they kind of straighten back up again.
Right. Yeah, and that's just it's a launch tower avoidance maneuver to keep it from bashing into the launch tower, which is a good thing.
So here is like the first dashboard that comes out to give an idea of the indications of what's going on, what the speed and the altitude. We can't tell anything from the altitude because they only show it in kilometers, so we're not seeing it in meters. We can see that 3 are out, and we can see that the locks in the methane tanks are, I mean, they're maybe 90% already. I mean, it's sort of like usually about where our Teslas are when we take them out, never at 100%. So
also, if you look at the attitude of the rocket right there, you can see it is very slightly tipped over. So it appears to be showing a slight angle to the horizon going on there, and it starts to go up, and everything seems to be sort of okay, and then you end up, I think here, usually somewhere right around here, you end up getting what seems to be definitely something going wrong right there. Something runs at that point. And we continue up, and there's speculation, so that's around the 32-second mark, something like that, that it might be the HPU, the hydraulic power unit. And that's what powers the gimbal on the rocket engine. So that means you've lost thrust vectoring if that is the case. And I will go on record saying I do not believe that, because I think that the rocket would have gone out of control at that point personally. I'm wondering
now, this wiggliness here, that's just optical. It's not the rocket going out of control like was just speculated. I'm kind of wondering as well is whether that goes out, what they could do, and whether there's like robustness enough in the system that you could start to control it, not with gimbals, but now with thrust vector, the throttle up and throttle down. Right. Is, you might be able to, if that contingency is in there, but it seems to go through it so smoothly without even a hiccup. You kind of wonder, is there really that much sort of momentum and inertia? Well, also look at, wait, look at 41 seconds or 40. Yeah. You see the other engine go out right there. And so I think it was just that engine running. Like it could be. It could have been. So you end up getting right there. Yeah, you can see that engine goes, and I believe there's actually two of those engines are out. So the graphic only shows one, but we end up seeing later on when we get the bottom view that those 2 engines are definitely out. So it could have been caused by that point. And there seems to be a delay in this telemetry. Now, this dashboard here is something that's on the live stream, and it is getting information from Mission Control in Hawthorne. It is not Mission Control in Hawthorne. So that means the data we have here could be already filtered a little bit and also perhaps behind. So you can't trust it 100%, which we're going to see just a little bit. So as we go on up here, we'll begin, we get some brightness, which might just not be a RUD, but could be parts falling into the exhaust at that point, making it a little bit brighter, And here is where we end up seeing what's out right now. And so we were able to compare that with the graphic, and we're able to see there's actually one more engine that's out at this point.
Also very interesting. Where did it actually happen that we saw the representation of? There's the one at like 9 o'clock on the display. That went out relatively, I don't remember what time exactly that one went out to.
Okay, so this one here, the one that's at 9 o'clock right now, when did that go? So right there. So it goes.
Yeah, okay, exactly, so that's later than the other one.
Now this is, okay, thanks for having, let's going back here, because this is an interesting point. I think I had speculated that it's like right around the 56-second mark that you really know that, okay, it's all over. Up until then, you might have had some hope that's going to make it. And the reason is, again, look at these LOX tanks here. Now, this is supposed to be close to max Q. And I think I hear them doing a call out that, now we're starting to power up. So in theory, they're powering up right around here. What I want you to do is look at the LOX tanks and look at the C4 tanks. The CH4 tanks. All right. So we come in here
and just for a note, they should be going down at the same rate.
Yes. Obviously. You see how quickly the LOX tank goes down? So it suddenly drops really quickly. And that maybe that means there was just something wrong with the sensor and it finally got the real value or a little bit behind. But it seems like it went from to suddenly a lot less in a hurry. Right around there. So between 56 and I think like a minute, 2 or somewhere around there, there's that big drop. And then we get these other views and we start to see what is either more rutting or more engine rich exhaust. Right. Okay. So then we kind of continue up and, we're beginning to notice.
Stop right there. Yeah. So one interesting thing here is look at the position of the rocket and then the contrail. Yes. It looks like the contrail should be coming out directly behind it. It certainly looks like it's coming out at an angle. Which means that it is skidding through the atmosphere rather than really getting out of there.
Yes, it starts getting worse and worse. Now we're getting close to 2 minutes, and this is supposed to be where we're going to get the staging. And now here's something I want everyone to sort of notice at this point. So we are seeing the rocket is pitching over. Right. So it's pitching over more and more, which you sort of want to. Once you get above the atmosphere, you need to go a bit more horizontal. And you'll sort of see the attitude of where it is right now. And now out here, we can see, and this, I believe, is right around where MECO is. So they probably have shut down, even though it doesn't look like they've shut down the engines, I believe they have at this point. Now you can begin to see that the rocket is rolling. Yeah, which it definitely should not be. Right. And you can also see it by the way the light starts dancing around inside there, because there is actually light from the outside coming in through over here. See, these are the grid fin controls, right? So that ring of white there is actually outdoor lighting coming in. So you'll be able to tell if something is changing. If you're moving around, you'll get a little bit of that sense there. And if you look down here at this indicator here, it suddenly flips around 180. And what is happening there is that is a math error. Right. The rocket did not actually do that. What happened is that there's two solutions to yaw, pitch, roll. And depending upon what the attitude is, and the best way to explain it is, I've asked you this before, John, what's the square root of 4? Right. Well, it's 2. Or -2. Or -2, yes. Yeah, see, I got you again, all right? So it's one of those things. You got to be careful which solution you're choosing. Yeah. And so it seems that what ended up happening is that when you get into that roll state there, you get kind of what they talk about somewhere with these matrices that you might get into a gimbal lock situation. It becomes very difficult to actually come up with a proper solution, and your solution will suddenly flip. And that's what's happening here is the rocket is actually pointed in that direction. Right. Let's just say the angle with respect to the horizon here is correct. It's just that it should be the opposite one, the complementary one. One other interesting thing is that they've still got quite a bit of LOX and CH4 at this point, which means it may not have been burning. You should probably have a very little bit left. You should be out. You would think you would be out if you were actually burning it all up, up to that stage. Almost out. To. Like, yeah. Now I'm speculating that, this live stream here is not mission critical. This is something that gets grafted on top of everything else, and it's not tied in. And it may have been like an intern or someone who was tasked with coming up with this this dashboard. So you never know how reliable any of the data is there. And again, that that little calculation there was clearly someone didn't quite know how to take the correct square root or how to use the ATAN2 function. So we're going around there, we're getting that error, and we're noticing these things are starting to drop. We're getting close to the apogee. I think the apogee is around 39 kilometers. At this point, it's no longer powered flight. It's ballistic. it's going to go up another 4 kilometers, but just through pure momentum.
But also the speed, if you're looking at an orbital launch vehicle, 1886 kilometers an hour is very low for the first stage.
It's not much. It's not much. We can see the speed is dropping at this point. So I think it may have maxed out close to 2000.
Yeah, I think it was like 2100.
It's up a little over 2000. And then, that's basically the engines are cut off. And now you're starting to slow down because of drag and because of gravity. And remember, this is the speed of the vehicle going through the air. It's not the speed of it going up, and it's not the speed of it going horizontally, but it's actually its forward direction. And now this is where it gets a little bit interesting. I believe right around
right there. Here, I think you could see it.
Right at, basically at 314, basically pi, so I put the shirt on to remind myself. Of course it was. At 314, you begin to see these 2 streamers up here. Now, can you see that pretty well? Or if I kind of bring this around and in, we can begin to see a bit better what's going on here. This is probably the FTS being initiated.
Right.
So evidently they are small explosives on the size charges over the tanks. And we thought those might have been cold gas thrusters. And we were kind of right. They are cold, they are gas, and they are thrusting, but
they are not intended to be cold gas thrusters.
Yes. So they are venting out at that point. So that's happening at about 314. Right. And so then that means it's going to continue on up here.
So the intent, just for the FTS is a flight termination system. It's supposed to explode the vehicle, but what they've done is they've punctured the methane tanks in both the booster and the Starship, but it didn't explode.
Yes. It definitely did not explode. And so we can begin to see it here. It is venting, and it's just waiting for an ignition source.
Right.
I think those are the methane tanks, because the oxygen tanks we determined are lower and the methane tanks are a bit higher. It's just that at some point we finally get combustion that's going to happen somewhere around there. And then the first one combusts.
Boom. Yeah.
And then the second one is going to combust. I think that's the first one. And then the second one comes a little bit after that. Or maybe that was the second one. I have to see. There's the first one.
Yeah, the first one is more of a flame out. The second one's a full-on explosion.
Right. Okay. So that's just, I think, fixing maybe some of the things that we had discussed in the first video and clarifying them and maybe making sure they're correct.
Yeah, the really interesting thing to me is the FTS, if that is correct, that those 2 holes punch, number one, that it didn't explode immediately, which is really interesting.
Right.
And number 2, that they did it at a little over 3 minutes. And so it took a long time for it to decide to ignite.
Yes. Yeah. So it took, I think, close to 50 seconds more. I mean, some people are saying the command may have gone out sooner than that. But I'm just saying it's happening at 314 because that's the first time we can see some signs of some streamers that we know something has happened. So I don't know what the delay is between them pushing the button and it finally getting out there and us being able to see it.
And I mean, this is total speculation, but SpaceX being SpaceX, they always want to do it in the most minimalist fashion. I believe in the old days, the FTS was kind of it was like a pyrotechnic line that went up the whole rocket ship, and it would unzip the rocket, and it would basically just unzip. And SpaceX was probably like, we don't need to go that crazy. We can just put 2 small explosives on the side. And clearly it did not work efficiently if that was the case. So, and now we get to play with graphs. Yay.
Yeah. Now here's what I did. So this is about as nerdling as you can get, is going all the way back to here, is that it's not until 14 seconds that we see the first value show up on the dashboard. So we have no idea of telemetry until right about there. So I downloaded this thing, and when these things exactly switch over to like 14, 15, everything I'm recording, actually I did it in half-second intervals along the way by going to different frames. I was just taking the speed in kilometers per hour here. The altitude is almost useless because it only counts in 1 kilometer step. So you really have no idea what it is. So I just decided, all right. And I did this once before for a Falcon 9 launch, so it's not the first time.
Actually, do you have that up? Because it would be interesting.
Yeah. I'm gonna bring that up in a second.
Okay.
So we have it like at 14 seconds that this is exactly what the kilometers per hour. I then just turn that into meters per second, and then I need to have 2 time steps here, so we get another time step there, meters per second. And if you take the difference between this speed and that speed and divide it by your time step, this gives you the acceleration, meters per second squared.
Right.
That's the definition of an acceleration, is the change in velocity over time. And so that's what's happening there. It's a very simple derivative. In this case, it's a numerical derivative.
Right.
And
it's important to understand that you are automatically subtracting the force of gravity, which is 9.8 meters per second squared. Because just to hover,
so
it would have
here,
to be putting out 10 meters per second. Yeah.
I take that, and just to kind of put it in, so 2 meters per second squared is about 0.2 Gs. So the idea of how much over gravity. So it would be considered 1.2, but it's really this value here that we're going to graph. And I just want to get an idea of whether we're ever going above that. And then here, I'm calculating kind of the distance traveled. I have to be very careful. So it's very easy to do that integral. If I know the speed, and if I know the velocity, or I know the acceleration, I know the velocity, you can keep on calculating how far it would have gone. And at first it's going straight up. So my numbers and the numbers they have are going to be pretty close. And then at some point they're going to diverge because the vehicle starts doing this, and I'm just assuming it's kind of going straight up. So we'll see that when they first post 1 kilometer, I'm pretty close. Yeah. And then when they finally come to 2 kilometers, we're getting pretty close. And then at one point it flips around that because they start going horizontal, I'm starting to say, well, you should be at 6 or 7 kilometers sooner. And then I end up getting it out like it probably traveled 40 kilometers or something like that. So we can get that. Now, the main thing is, like, let's take a look at this acceleration curve here.
So this is graphing column E? No, D. Column D. Column D.
Column D, yes. Yeah. So we're looking at column D.
Over time, yeah.
And basically, when you get up around 10 meters per second squared, that's about gravitational acceleration right there.
Right.
All right. So you'll notice here that it seems like there is a heartbeat and that the values go way off. And the reason why the values go way off is that for some reason, in one time step or something like that, like right around here, you'll see that the velocities seem to be the same. So it's almost like, wow, the acceleration just dropped down to nothing. So you see around here, we have the acceleration about 1/3 G, somewhere in that area. And suddenly it starts to fall, goes to 0, and then jumps up to over 1 G all of a sudden.
Right.
And then drops down to 6, and then kind of settles back down to where it was. I suspect that's something to do with the data that's being pumped out to the dashboard. There's a lag going on in there because it seems to be happening always at the same time. And then I made some attempts to try to clean up this data to get an idea of what it's supposed to look like. So that's what happens here in the next sheet, that I have more of the raw form. And then I do something where I sort of average the speeds from before and after. So it's like it's not a 7-day moving average, but it's kind of like that, you know.
You're basically doing a
2-second moving average.
Filtering.
Yes,
yeah,
a little bit of filtering. And I was surprised I'm still getting this bump in there, but that's just the data transmission. But we can see the trend here. So the trend line is going along here, and it starts to go down here. Right here, that's when the LOX load suddenly dropped precipitously. That's right around the 1 minute mark in there.
Yep.
And then it seems to come back up. Now, what we're seeing here, this is a trend I would have been expecting earlier on. So you see this sort of monotonic increase of it as we going through here. We're getting more and more acceleration. So in theory, we're applying the same thrust the whole time, but the vehicle's getting lighter. And as it's getting lighter, it's going to accelerate more and more and more. But at the beginning, we don't see that. We see that it has what is about 0.35 Gs, or I guess about, like 3 meters per second squared of kind of acceleration, which is about what you would actually expect. Because I was saying is the thrust to weight ratio is 1.5, and you take 90% of that, you get 1.35. So we're right around there on what we would expect. And it seems like it's increasing a little bit, but then it just doesn't keep on increasing, and then it drops off in here. Now, this dropping off, it could be because things are starting to go bad, or there could be another reason. And I'm going to contrast that with.
Can you, like, where did they hit max Q? Because was that right around the 1 minute mark?
It was supposedly right around the 1 minute mark, which seemed kind of early to me.
Yeah.
I mean, their altitude wasn't there. So if you look here, this is a typical Falcon 9 launch.
Right. And you got that bucket that's
again, I have some little problems there with, like, the noisiness in the data and right at the beginning. But you follow that and you'll see that the thrust increases. Now, right now, we're right here. That's like around 35 or something like that. So here's 50. We don't really exceed that at all with Starship. I think very late on we get in there, but you see early on with the Falcon, we get up to here, and this is what's called the throttle bucket.
Right.
This is when they intentionally power down because they're getting very close to max Q. They pass through max Q and then they throttle up. So this is normal.
And also you could theoretically draw a line right through that bucket, and you see there's a very consistent acceleration that's monotonic.
Very consistent. Yeah. It's just that right here, the atmosphere is still pretty thick, and your velocity is going up, fast enough, and drag goes as velocity squared. So every time you double the velocity, you get 4 times the drag. So it's like right around here, there is absolutely no advantage to pushing really hard. You do want to kind of drop off,
and of course the disadvantage being that you can tear your ship apart because those are the maximum stresses.
That too. You're going to tear it apart, but you're also in a sense wasting fuel, because all you're doing is all that energy is rather going into potential energy to lift the rocket is going to energy to heat the atmosphere is what it's doing. So there's also another reason: one, to keep your rocket together, and second, it's just optimal. That's the optimal way to get the most out of the performance of your rocket. So you drop through here, you come up, but you see it increases, and we go well over 30 here, which means like you would be feeling 3 Gs kind of pushing on you, or 4 Gs altogether, because you get the 1 G that's down. But that's what you're going to see until you get it. It should be going up, and you should not be getting this kind of peaks and valleys and everything else that we end up seeing in the other. So when we come back to here, I don't know if this was their attempt at a throttle bucket, because if it was, they didn't need one. They were performing so bad. We're not getting over 5.
Right.
We should be getting 5 already. About, if you were to follow this trend line, I would say they should be hitting it somewhere about here. Right. But instead, they're losing power. I mean, they're losing a lot of power here that you're almost wondering whether it's able to hold itself up.
Right.
And then you come back here, and now they seem to be able to have almost a consistent power, but they're almost not consuming the fuel fast enough.
Right.
So they're not getting light enough to be able to get the advantage, because as we can see, the tanks look like they still had, an eighth left in the tank by the time they finished.
They were not planning on trying to soft land the rocket, so they were probably just going to burn it all. So they just did not get through the fuel. They
So they were not getting through. And again, 30 is way up here.
Yeah.
We don't even cross 10.
Right.
We don't even get close. So the closest we get is about 3/4 a G, 0.75.
So, and again, like if you go back to the Falcon 9 launch, you could see the bucket happens, and then it goes back to, like, if you imagine that acceleration curve without the bucket, it's like a line.
Just before the bucket, this is about the maximum we'll end up seeing out of Starship.
Yeah, but the problem is when the Starship comes back from the bucket, it's way below that. It doesn't continue that upward. Yeah, and then it doesn't cross 10. Yeah, does not cross. It only gets up to about 7 or 7.5. Right. So it way underperformed. Yeah,
definitely way underperformed, and I think we have the numbers to kind of prove it.
Yeah, which is really fascinating. Okay, little addendum here, because we were looking at this after we got done, and we decided, we're like, there is this possibility. And Scott, I'll let you state what it is.
We'll splice it in. So this is future,
I'll just splice this in,
John.
At some point. Yeah, there we go. So go for it.
Yeah, we're looking at this here, and we're seeing that the thrust is increasing right along here, and then you get around that 30-second mark where the HPU allegedly goes out, or
slash one of the engines.
One of the engines. So you start to lose some power here. And it's going down, and we're not sure if this was supposed to be the pre-programmed thrust bucket or not. And then right in there, suddenly they lose a lot of mass, and then it seems to all of a sudden get better. So we're wondering if the performance is just degrading in here, because it's just degrading, and that you need to get rid of a lot of mass in a hurry. And then it starts to pick up. And the analogy that we came up with is like the hot air balloon and all those scenes where they're losing altitude and they start throwing everything overboard that they have, the shoes, the wallet, the glasses, the watch, all the mass. So maybe this is what's going on here. It's not a throttle bucket, but it's the hot air balloon rescue mission right in there. That pure speculations, probably has nothing to do with it. But
it could be a combination. It could be a combination of both. Also, the other thing is, if you flip back to the Falcon 9 profile, just hold on this for 1 second. So you can see that the orange line after 61 seconds is flat to almost curving downward. And now look at the Falcon 9 compared to that when you flip back.
And the Falcon 9, you definitely get this other effect here, that this is more of an exponential. So it's not really a linear increase, but you see it slowly is going up
Right.
higher and higher the whole time.
Right.
So the
And
slope is
again,
getting, and that's what you should,
the
that's
same
what you
amount
expect.
of thrust, and the thing weighs less and less and less and less. So
Right.
obviously it's going to accelerate
Right.
faster and faster.
And that's what you're going to get, because the way the mass distribution and everything drops, you would expect it to kind of go up. And eventually, you know, if you're able to take the mass all the way down to zero the last second, you're going to be right up at infinity.
Yeah.
But you never quite get there, obviously, because you're going to have, you know, structure and everything else around there. But you will be seeing that, and we never see that. Well, what we see is the opposite. Is it's trying to, it's more or less, it's cresting a hill as opposed to going up the lower steep part.
Right. Yeah. If you go back to the other one now,
we go back and we can see that. It's like
and
it's
see how
trying
it
to
doesn't
climb up the hill, but
it's not a U shape.
falling
It's
off.
more of a humpy shape.
It should be going up, and it could be that losing that mass there is what allowed it to kind of turn the corner and get back going.
Right. But at any rate, it should have been going upward very rapidly before the main engine cut off, and it was not.
It was not. It was not. There's really no good explanation, because if that was a pre-programmed throttle bucket, I would expect it would kind of come along here and then have a sharp drop.
Right.
And then it would hold it, and then it would go right back up.
Right.
Which we saw in the Falcon 9. And this is more or less like losing power, losing power. And then suddenly a little bit of
again,
recovery.
if you look at, so let's say we had about 4 meters per second squared acceleration at about 31 seconds when that one big flame out happened.
Yes.
Before we get to 4 meters per second squared again, it's somewhere around 79, 80 seconds, somewhere in that range.
It's way out there. It's way out
I mean,
there.
maybe even longer. So it had to lose a lot of mass before it got back up to that acceleration.
Yes.
Again.
Yes, took quite a bit. So it was just enough to get it around that little hump.
Right. So anyway, so if it had gone too much worse, it would have started negatively accelerating, which would be bad. So if it had crossed that 0 mark, that would have been really bad.
Mm-hmm.
So anyway.
Agreed.
Yeah. Okay, well, cool. Yeah, so we just wanted to insert that because it's actually really interesting to look at that and kind of analyze.
And this here, everything goes negative because that's when the engines have been cut off and it's falling.
Right.
That's why.
But still, weirdly enough, it actually looked like it had some acceleration down there. It's kind of
this is where it gets weird. That's when the thing is flipping around and who knows what's happening. So
so the data
probably
is just bad data.
Mess. Yeah, it's a mess there. That's why I stopped looking at any more of the data, because like, it's not telling me anything. But that's what you're expecting would happen, is that when the engine's cut off, you're just going to start falling, and then you're going to see your acceleration suddenly go negative.
But, again, not taking anything away from SpaceX, because this was an experimental launch, but clearly it did not perform as expected.
Yes.
The whole way.
And I'm wondering why. I was expecting that we would have been at least getting up around 15 to 20.
Right.
And to see it so low, I mean, okay, there was a couple of engine outs, but it means those other engines were probably way below performance level.
Right.
Way before us. It wasn't just like, there were 7 that were out. That's why you just do the simple math. Now, even with 7 out, they should have been able to easily get above 10, 15, maybe even 20.
Especially as they got later into the profile, because of course the ship weighs less and less and less.
Oh, weighs a lot less at that point. Yeah. Yes, a lot less. And then, the other thing might just come down to their ability to control the vehicle. Yeah. It may have been that it was so compromised that they couldn't really power up without losing complete control. And again, we were talking about is that it was sort of the asymmetric distribution of the thrust. So the way to imagine it is that anyone that's used to like canoeing or crew or something like that.
Here, wait, let me stop sharing. Actually,
let's go ahead and stop sharing.
Yeah, just so, because you can wave your hands more effectively.
Yeah, I can wave a little bit more. Or let's go to Greek mythology and what is it, the trireme or something like that. You get all the oarsmen, right? So in order for the ship to go straight, you have the same number of oarsmen on each side. And so long as they're the same strength, they're all going together, the ship is able to go straight. But if 2 of them break their oars right at the beginning and everyone is going the same, the ship is going to start to kind of go off the side, and you need to correct that. So the only way to correct it is to make the guys that, are on the other side go maybe not quite as fast.
Quite as hard or something like that.
Quite as hard. Or I don't know if you can, like the ones on the side where you're short the 2 oars, where you stick the oars out a little bit more to get a bit more leverage. That would be like the equivalent of having your thrust vectoring. But if you can't do that, then what you have to do is you have to kind of control the amount of power you're putting on one side or the other. And this is what was happening in Starship, is we were losing most of the engines kind of to one side.
Right.
And so that meant it's going to be skewing it a little bit. It's pushing a little bit harder on one side, a little bit less than the other. It's just like we'd be doing with the rowing. So you have to back off on one side or try to tell the other side, row harder, row harder.
Right.
But they're probably like, no, we can't do that because we're going to compromise them anymore. And the only other choices it might be is that as you start to do that, it means you're kind of drawing them all down. It's not like you can suddenly make one side go 120% to make up the fact that another side's at 80%. It's like, nope, you're capped at 90. If you're going to have to bring the other side down to 70, that kind of brings your performance down.
Well, and it makes good sense too, because that means that they wouldn't burn through all their propellant, right? And we saw a lot. I mean, it looked like maybe 20%, 15 to 20% was left, according to that little graph that was there. So
if you could trust the graph, I've learned to never trust a gas gauge on anything, especially a boat, when things are sloshing around, because you'll go out in your boat in the morning, and if you don't look at it when it's still, it might be showing there's like half or even a quarter. And then you take it out there and like everything sloshes back. You're like, how much gas we got? Oh, it's 3/4 full. We're good enough to make the day. And then, a few minutes later. So yeah, it's a bit tricky. I don't know how they are measuring it, whether, I know they have cameras that are looking in there. At least they've shown shots inside. I wonder if they're almost trying to look at the level from that and then try to determine what it is. Because there is kind of a meniscus. In the past,
I've heard they just have ball measure, just like what's in your your gas tank is just a little ball that just
that could be.
As it goes down, it knows, because it's under power the whole time, so it's got gravity.
In theory, so that's one way of doing it, but I've learned not to trust it, and that's why I was wondering whether you were getting that sloshing around. But when they went into that quote throttle bucket, they're still pushing up, which means the oxygen is not floating around. It should still be at the bottom of the tank. And just because they power it up shouldn't do anything. It's not like it's going to suddenly compress the oxygen that you would see it fall like that all of a sudden. So something a little suspicious was going on there on why they lost the O2 levels really quickly. And again, it could just be there's something along with the telemetry, or again, there's something wrong with that dashboard that it's getting the values kind of late, or they're getting interrupted along the way.
Yeah. The weird part was it definitely was above the CH4, and then it went below. And then by the end, they kind of were almost back to even. So it seems like with the way the O2 was going down, it would have just gone and been gone.
Yeah, but near the end, the O2 just went right to zero.
Oh, did it?
And then the methane, you still had, I think, about a sixth in there. Yeah. And so right near the end, it kind of cleaned itself out finally after because you begin to see that when they do the detonation, the levels start to go down again. So the levels were fixed, and then the FTS goes off, and then you start to see it. And it seems like the O2 levels went a lot quicker than the methane for some reason. Even though it looks like it's the methane tanks that were the ones that had the
You would think you would, well, maybe they do the O2 because they figure that will actually combust with the explosive, but I don't know. Weird. It's weird.
Well, there should be more than enough up there. I mean, because they were still in the atmosphere. So there's more than enough oxygen, as we could see when it finally went. It doesn't hurt to have the liquid oxygen around there to make it go. But the reason, part of it is they want the tanks to collapse.
Yes.
And the thing is, the pressurization was working too well, and they had too much already in there that then they really couldn't, the tanks were not collapsing like you're supposed to. Right. So it's like, just because you stab the Coke can and stuff is spraying out doesn't mean it's just going to collapse right away. You have to get it down enough, and then it goes. And that's what happens. Finally, you get the buckling.
That's for people, again, if people don't know, they have what's called exogenous pressurization, if I'm remembering correctly, which is that the ship itself, they don't have separate nitrogen gas thrusters inside the ship. They actually are using the tank pressure itself, which is very clever because it gets rid of a lot of stuff. And I think it was Tim Dodd, I think it was the Everyday Astronaut, who suggested that, and Elon was like, that's a good idea.
They were saying something. It's because in order to run the turbines, you have to burn some fuel to run the turbines, which means you have an exhaust product. And the question is, what do you do with that exhaust product? The Saturn V was very clever. They found a way to actually kind of get it in through the nozzles and use it for nozzle cooling. But in other cases, sometimes they just dump it off to the side. So you have this exhaust product. The other thing you could do is you could take the exhaust product and run it all the way back up to the top.
Oh, no, this is full flow. They don't have to worry about that because that's all going into the exhaust. Okay. So I'm just talking about they're not bleeding the pressure inside the tank. The tank is like a soda bottle.
Yeah. So I think
they're just using the extra pressure.
They were taking some of the heat, or they're taking some byproduct where the heat, and they're dumping it back in there to actually increase. Because normally they use helium. So usually that's what the helium tanks are for, is to allow the pressurization.
Right.
And
yeah, you might be right. Well, either that or else just the fact that methane is cryogenic, it might be heating up naturally. So they might, I don't know. I don't know exactly how they're doing it, but whatever it is, it's heated with methane inside the tank, which is pressurizing it.
Which is
it's not using helium, it's not using nitrogen.
Basically, it's heating, it's almost using the fact that you're heating the product up, of course, is going to create the pressure.
Right.
And that some of that was for also the thrusters, which are, as we know, are not cold gas thrusters anymore.
Right. Yeah, they're semi-warm gas thrusters.
right, which will give you definitely better performance, which you might need for a vehicle of this size. Because I think Tim Dodd showed a picture of it. He now actually has like the 2-scale models of a Falcon 9 and a Starship next to each other. And wow, it's like, when you put the two next to it, it's like, that is a big beast. You don't realize it. I mean, if you've been near it, the Falcon 9, it already seems pretty big by itself.
Right.
When you stand next to it. But then to imagine that, wow, it's small compared to this.
Yeah. I don't know if anybody's gone to Kennedy Space Center, but they have one of the booster sides from the first Falcon Heavy launch, and it's big inside that interior of the space. It's like, whoa, that's a big rocket. And then you're like, that's dwarfed by the Starship.
It's absolutely dwarfed by it. You're right. So it's yes, and that's what happens when you scale things. Like, you just can't scale them in one direction. You have to scale them in two. Right. So when the diameter goes out, man, it's like, it doesn't just go as a linear function, it goes as a square function. So now you realize that's a lot of Falcon 9s that you can fit in the first stage.
Right. Yeah, I need to get that because I have the Starship back there, but I don't have a Falcon 9 to scale. It'd be really cool to have
that. It's pretty teeny.
Yeah. But anyway, so obviously, if the FTS went off when you and now I think is correct, which when we saw the streamers around 3 minutes or so, that punctured the tanks, but because they're so overpressured in there, that they're not becoming empty and like low pressure at that point. They still have a lot of pressure, so they're just like, so the tanks didn't collapse. And there was no combustion source to ignite it.
And for comparison, if we go to the Chinese weather balloon.
Yes.
And the idea is like, why couldn't they just do a strafing run of the balloon and just put a bunch of holes in it? And it's like, yeah, they could do that. The thing is, it would take so long for that volume of gas to leak through those small holes. So that's part of the reason why they just had to go in and actually hit it with a missile to take it down. Same thing there is like, even though you put a hole like that big in there, it's pretty small compared to the volume that's there. It takes a long time for it to come out. It doesn't come out. And as we can see, it takes like a minute for it to get to the point that was maybe either enough for the structure to finally collapse under its own weight, or we had an ignition source to finally let it go up. And then once that happened, of course, it's going to rip apart.
Right. Yeah. And the interesting thing is this is another data point for SpaceX, because this means they need to increase the capabilities of their FTS. Because if they needed to do this 1K off the ground, like just after it launched, that's not great that it took that long for it to explode. It needed to go up, just disappear instantly.
Exactly.
So, yeah.
They need to go a lot quicker. So
they probably need a match.
Decision they make.
They need a, what am I thinking about? There's some movie or something with like a monkey holding like a match into like a maelstrom, but they need somebody to light the match after they punch the hole to like set off the ignition. So
they need the ignition source. And I'm assuming that that's not solely their decision. Like, oh, yeah, we're just going to do it. They have to get some sort of certification from the FAA that they actually have an FTS system. And that's probably one of those things that's going to be looked into and may delay. I mean, I know Elon is thinking that, they're going to launch again in July. I'm not so sure. There's still a lot of cleanup they have to do. First around stage 0, and then second, whatever that redesign is going to have to change quite a bit.
Yeah. And I will still point out that I think that a moat, like what was it? The mega
oceanic acoustic tamper.
Yeah, there we go. The moat. Yeah, but I think I posted this on Twitter. I'll put a picture of it here or something. But I think that it's a good idea that because I think what they said was just at the exact same time, Elon said that they'd been working on this metal plate, water cooled. So I don't know if that's internally water cooled or what, but I guess the idea is they're going to put a big giant steel plate underneath the launch tower. But I think our idea is, I think a moat is a better idea. Just a big giant tank of water that that's refreshed, and it just naturally is filled with ocean water. And you would have to put a sprinkler system on top of it because you don't want a perfectly flat surface when it launches, because otherwise you get perfect reflections off of it. But as long as you had, some sort of bubbler or something like that was making the surface uneven at launch, it would be fine.
Yeah,
But
and I think, Zach Golden showed a couple of pictures of them launching out at sea, and he's thinking the solution is going to be the platform out in the ocean.
right.
And you don't have to worry about it.
Well,
and the thought is like, well, wait a minute, rather than going out of the ocean, why not just, the ocean's right there, kind of invite it in, make a little lagoon around the thing, make it deep enough. Maybe, you're probably going to have to put something like some gunite surface underneath, like you would in a swimming pool, fill it up, I don't know, 15 meters deep or something like that. Because the whole thing is the Army engineers, everyone's going to have to sign off that you can actually go down the water table to it. But if you do that and the whole idea is just filled with water, then that would probably take a lot of the force and then would just sort of vaporize at that point.
Exactly.
And you have that steam cloud, which is fine. And then just give it the Bond villain feel, is that when they're actually working on this thing, of course, you would have this floor that closes over it. And when it's time for the launch, you just come out and you reveal the fact. And then, of course, we want to make sure there's sharks in there. So it's
exactly.
Shark
There
Tank
have
at the
to be
time.
there have to be sharks, because then we get Sharknado when it takes off.
Yeah, exactly, when it goes off, because obviously the launch created the tornado yesterday down in South Padre. No one started any rumors here or anything like that. But it's
so I mean, people have talked about Boring Company and stuff, but it's like the problem is that you have to do what NASA did at Kennedy. And you have to lift it up to create a flame trench, because they had to build it. And then they have all of the complexity of getting out to this. It seems to make much more sense not to worry about a flame trench, but just utilize the fact that you're on the water table and it's going to naturally fill up with water, and just fill it up with water. And you might have to make sure that it's not brackish, it's more fresh water, so it doesn't get salt all over the place. But still, I mean, I think that's much more doable than trying to figure out a flame trench or build this thing up.
It's basically, it's just going to be a big hot tub right underneath, and that you just warm it up.
Wait, you suggested this, that what you should do is sell tickets afterwards, after the launch, like an hour after the launch, you get to go in after it's not boiling anymore. It's come down in temperature. You pay big bucks to go hang out in the hot tub that was the launch.
Right. Yes.
So there you go. Those are good VIP tickets.
Yes.
The post-launch hot tub. All right. Well, thank you for doing all that analysis. That was that's actually really cool to see it in graphical form and to realize just how underperforming it actually was.
I was surprised, because like the quick analysis I made, it's like, oh, it had the thrust it was supposed to at the beginning. I assume it continued all the way through, but as you can see, it just that was the best it could do. I remember when the serial number, 8, 9, 10, 11, all those ones that went up, and how they would go up so slowly, and you just see like all the, the smoke and everything just kind of flowing around the ship, because it wasn't really, this thing looked a little bit like that. It looked like it wasn't going fast enough to be getting away from all the stuff it was creating. And that's the thing, it's hard to tell because it's so big. Sometimes you were tricked into thinking it's not moving fast, when actually it is, because it's so big.
Right.
But no, it was moving pretty slow, because it took, when I was going through the numbers and just kept on putting them in, it's like, when are we going to get to a kilometer? I mean, that kilometer's not that high. I'm just going on and on. It's like, I'm trying to think, it's like, at what time did we actually hit a kilometer? It was pretty late in there. It's I have to go ahead and look on the sheet, but the first kilometer came at about 30 seconds.
30 seconds.
28.5 seconds.
Crap. That's a long time.
Hitting. Yeah. And remember, they didn't clear the tower until 14 seconds. Okay. So, so once you clearing the tower, it's taking another 14 seconds to be able to go 1 kilometer. Yeah.
Yeah. That's pretty slow. I mean, if you compare that to the Falcon 9, because once that clears the tower, it's out of there. If you've seen a launch in real life, it's impressive. Once it gets going, it's just like,
yeah. And the first thing is like, man, it takes forever to clear the tower. Is everybody going to clear the thing? That first 6 to 8 seconds, it just, you cannot believe it's going to start picking up any speed if it's that slow. But then they probably are powering up a little bit more after that. And the fact that they've burnt off so much mass, it makes it a lot easier for it to accelerate. And they actually have to pull it back, because I think the maximum that the Falcon goes is, like I say, is about 3 Gs of acceleration.
Right.
And it's a lot of times because the payloads that are in there don't want to have more than, like, especially human payloads don't, they can go more than that. But right now they just said 3 Gs is comfortable. We don't want anything like that. You might have some satellite payloads that don't want to go through more than that. But if they wanted to, they could get it up 5, 6, maybe even 7 Gs. When it gets really light at the end, they could just really be pressing it. But as it starts getting light enough, they drop back. And the second stage is the one that can really, can really go at that point, because there's almost no mass left.
Right.
And when it gets to the end,
Well, I mean, look at so all of that gigantic first stage on the Falcon 9 is used to get to about 5,000 kilometers an hour, which again, in reference, and I don't know how fast the Starship was supposed to go, but it was about 2,100. So less than half. But anyway, that's 5,000. Yes. And the second stage, that little baby second stage on the Falcon 9 gets it to 25,000. So it's an extra 20,000 kilometers an hour. Now, admittedly, a lot of that is going sideways, so it's not fighting gravity as much, but still. That thing,
and not having to lift this, but yeah, you're getting a way more delta V out of that second stage than you are on the first part.
Got to get out of the gravity well.
So it was like it took a long time to break the sound barrier as well. So that was way up there.
And I think they may have actually called it early. You know, I think that there was probably a predicted moment of max Q, but it looked like when they called it, it was only going about 800, and that's significant. Maybe that is max Q for that. I don't know.
It's like, yeah, I mean, there could be. Because max Q is a function of the density and the velocity,
and also the structure.
If you go really, if you go really slow, let's see, then you can kind of push off where the max Q is going to be. But they had it kind of early, so it really comes down to that. The higher you get, the thinner. At some point, density falls off way faster than the square effect of velocity.
Right.
And so when you get to the upper atmosphere, it will drop off pretty fast. So you could delay it a little bit, but yeah, it took 90 seconds to get around right close to the sound barrier. And let me see if I can look at the Falcon, and the numbers I have there is when does it get up around there? It does it around a minute. Yeah, it's like around 57 seconds is the Falcon 9 is there. Right. So that was a big difference.
Right. Yeah, I mean, there's probably. We'll have to wait, you know, when we get Starship launch 2, 3, 4, then we'll have metrics that we can compare. So Scott will be doing this analysis for all of this.
All the
time. Just comparing the acceleration curves. But it seems to me like they had a predicted flight path and flight plan, and they bucketed it, but it was going so much more slowly because it was accelerating more slowly that the bucket actually came a little early in my mind. I'm imagining.
Yeah, and that's, I would think the control system should have been smart enough to know to adapt. It's like, oh, wait a minute, we're not there yet. Let's just keep on pressing. Yeah. But again, you might say it might have been kind of a pre-programmed bucket.
Right.
Ill-advised, there was no need.
They could have just kept pressing through the whole thing. It didn't really look like it needed it.
or maybe, maybe it was just also feeling a lot of stress, but I would have expected that there's certain amount of adaptation that the control system would have to pick up with the fact the engines are out, but maybe not. Maybe it's just like, no, just go for it. Just light that thing. Well, like a model rocket and see what happens. Again,
to give SpaceX credit, it's not like they're dumb or something. Nobody has ever launched this thing before. So they took a guess. They're like, here's what our simulations told us. This is the first time the booster had ever gotten off the pad. I mean, it had never actually left the pad before. So, they were guessing. They were doing the best they could guessing. And,
but some of that they should have pretty good control of exactly what they're. So that's, I mean, okay. I was going to say it's not rocket science, but no, it is. But
it literally is rocket science.
I mean, calculating what a projectile is going to be and the thrust profiles and everything is pretty simple. And you can do it in a spreadsheet.
No. But what I'm saying is it's pretty simple until you get failures of XYZ.
Yeah, until you get a lot of the failures and everything else. And a lot of the
thrust is less than you expected. So, there's a lot of stuff that they just might not have had built into we don't know how primitive or advanced the profile was. Anyway, I'm just saying, like, in case anybody at SpaceX is watching.
They didn't publish any milestones either.
Yeah.
So all there was, like, had a picture like takes off, goes up here, does a loop-de-loop, it's like, okay, there's a burn back, but when, what altitude and everything else. So I was trying to find where they were, and it's like, there was no numbers to compare this against. So just looking at that, I'm saying it really underperformed.
Yeah. It had to. It can't have accomplished. I mean, I think even if they'd had good stage separation, the second stage wouldn't have made it to orbit because I don't think it was going fast enough when it would have separated in order to make it. So, yeah. So anyway, that's all very interesting. So I'm again, just to make sure we're not razzing on SpaceX, they did the best they could. Nobody's ever done this before. It was very impressive. So we're waiting for the next one. Yeah. I would love it to be a month or two, but I have a feeling it's going to be 6 months before it decides to go again.
Right. But now we know why they said, if it clears the tower, we'll be happy.
Oh yeah.
And so they probably was like, they just weren't sure. And maybe it's the next versions have already taken a lot of these things into account.
Right. Right. And I believe that they're getting rid of a lot of the flaps on the Starship, so they won't have to deal with that because they're not even going to try to do atmospheric entry, like controlled atmospheric entry for a while.
Right. Right. So I think the next one, they just want to go up with a very ballistic looking kind of tip.
Yeah. So anyway, it'll look even more like what was the movie? Was it not The Dictator? What was that movie that they got the pointiness from? I can't remember, the Sacha Baron Cohen one. Anyway.
Yeah.
So anyhow, all right. Well, thank you so much, Scott. This was great. And thank you for doing all that analysis. That's had to have been annoying to type all that stuff in by hand, but at the same time.
I know I'm going to have to figure out how to get ChatGPT to like go through there and do this automatically next time.
Please read the transcript and tell me exactly when I'll
just read it and go ahead and put these things into Excel for me and calculate it all. I'm sure it can. Right. I'm sure there's some kid watching this right now. Why didn't you just do this?
Well, tell us in the comments, because it'd be a lot easier. Yeah. So there you go. All righty. Thank you so much. Have a wonderful afternoon, and I will see everybody later. Bye-bye, everybody.
Cheers.